This is lecture 9 on introductory quantum computing. So today we're talking more about control gates, and in particular how to construct them just using a control CNOT and single qubit gates. So this is something called decomposition. Essentially, we have a bunch of building blocks, and we're trying to use these building blocks to construct more general and more arbitrary circuits and gates. So one thing we want to do is to find a recipe for making something like this. So you have two qubits and one qubit controls the other one. And here, when this is one, an arbitrary single qubit operator acts on the second qubit. So it turns out that just using the algebra of 2 by 2 unitaries, we can construct something like this by just a controlled CNOT and a bunch of single qubit uncontrolled gates. So that's the task for today. But before doing that, I wanted to do a couple of examples to just get more practice working with gates and circuits. So one thing I want to do is, let's do this problem. So we're going to start with an example. And let's say we want to show that H, the Hadamard gate, then a CNOT, and here also there's an H. I want to show that this is the same as just a CNOT where the second qubit controls the first qubit. So if I have a CNOT where the first one controls the second one, then you put Hadamard gates before and after both. On both qubits, you put Hadamard gates before and after the CNOT. The claim is that these two would do the same thing. So we have different ways of trying to show this. So one way is to just take a brute force approach and try to construct the 4x4 matrices corresponding to these circuits and then observe that they're the same thing. So let's do that maybe. So what's happening? So first, when I hit two Hadamards on the two qubits at this stage, so let's say I have H, the operator corresponding to this will be H acting on the first one, tensor with H acting on the second one. So we know what Hadamard gate is. So it's 1 over square root 2, 1, 1, 1 minus 1. So the 1 over square root 2's give 1/2. And then we have 1, 1, 1 minus 1 tensor with 1, 1, 1 minus 1. So this thing is going to be 1/2. Then I have 1, 1, 1 minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1. And here I have a minus 1 multiplying that. So I have minus 1, minus 1, minus 1, 1. So that's Hadamard tensor Hadamard. What is the CNOT when the first one controls the second one? Well, so I know that when the first one is 0, nothing happens. So 0, 0 and 0, 1 go to 0, 0 and 0, 1. And then 1, 0 and 1, 1, when the first one is 1, then the second one gets flipped, right? The X, which is 1, 1, 0, 0. So C0 is really a controlled X, just changes 0 to 1 and 1 to 0. So this one goes to 1, 1, and this one goes to 1, 0. So if I want to write the 2 by 2 operator for this one, it's going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. So when the first one is 0, which is essentially this block, the first two, I have an identity, and when the first one is 1, I have the X, which flips. So one way to think about this in more detail is to say, well, 0, 0 is the first one, so it has a representation 1, 0, 0, 0. So I want this matrix acting on this vector to give me, again, the same thing, to give me 1, 0, 0, 0. So that means the first element would be, so I multiply the first row by first column, I pick this element here. Then the second element, I multiply this by this, and I would pick, again, the first element, right? Because here I have zeros everywhere. So, so I would pick this element of the matrix. Then for the next one, I would pick, again, I have the third row, this column. The only where I have a chance of getting something non-zero, because I have 3 zeros here, is if this first element is non-zero. So, so the answer would be like the answer, because I have 1, 0, 0, 0, it just picks the first column of this matrix. So, so one way to do this is then essentially just read off, you know, the result of the action of the unitary on basis states. So 0, 0, 0 goes to 0, 0, which is 1, 0, 0. So I put 1, 0, 0, 0 on the first column. The second one is 0, 1. Again, the second state has a representation 0, 1, 0, 0. So that becomes a second column. Now, this one, 1, 1 is the last one. So it has a representation 0, 0, 0, 1. So that becomes the next one. And then here, 1, 0 is the third one. So it has a representation 0, 0, 1, 0. So that becomes the last column. Okay, so we can read off from the action of the operator on the basis states, we can easily construct a matrix. Then what I want to do is to just see what the net effect is. So we have this HH, Hadamard tensor Hadamard. Then we have this C0, where the first one controls the second one. Then I have my HH. So what is happening? So first HH acts, then the C0 acts, then again another HH acts. So I'm going to get the two HHs have like, each has a 1/2. So I'm going to get a quarter from those two. And then the matrices I get are these. then I have this other set of Hadamard tensor Hadamards. So okay, so let's see what we get from here. So I just repeat all of that. So let's do this multiplication. So first row, first column gives me 1. First row, second column, again, it's going to pick the first element. Then second row, first column is going to pick this one. It's going to pick the second row. Third row, first column is going to pick the last row, 1 minus 1 minus 1, 1. Make a little bit more space here. 1 minus 1 minus 1, 1. And then finally, fourth row is going to pick the third column, the third row here. So it's going to be 1, 1 minus 1 minus 1. Okay. So if I do this matrix multiplication, first row, first column is 4. First row, second column is 0. I have 2 minus 1s. Fourth column, again, 0. Again, this one is 0. Now, second row, first is going to be 0. This one times that is going to be, so 1 times 1 plus minus 1 times minus 1. That's 1. But then we have 1 times minus 1, that's negative, minus 1 times 1, so that's also 0. Second row, third column is going to be, again, 0. And second row, last column, these are the same, so that's giving me 4. Third row, first column is 0. Third row, second column, 1 times 1, 1 times minus 1, minus 1 times minus 1, minus 1, 1. So that's 0. With the last one, again, these cancel out. Those cancel out. 0. Oops, what did I do? So we're doing the third row. So 1, 1, minus 1, minus 1. So if the first one is 0, with the second one, again, there's 0. With the third one is going to be, again, 0. No, that's going to be actually 1 times 1, 1 times 1, minus 1, minus 1, minus 1, minus 1. So that's going to be 4. And the last one is going to be 0, right? The 1 and 1 come with 1 and minus 1, minus 1, minus 1 come with 1 and minus 1, they cancel out. And finally, I have the last one. So this is going to be 0. This is going to be, let's see. Seems to be 4. And then the third one is 0. Last one is 4. Something is wrong. So let me check the second one. Yeah, so the last one, it seems that I have 1 times 1, minus 1 times minus 1. So that's plus 2. Then I have minus 1 times 1, that's a minus. 1 minus 1, so that's going to be 0 again. Okay, so that's the matrix we get here. So we're saying this circuit is just, I have one here, one here, one here, one here. So what would be the other, a CNOT where the second one controls the first one? Well, 0, 0, the second one is 0, so that has to go to 0, 0. 0, 1, the second one is 1, so that's going to flip the first qubit, so that becomes 1, 1. 1, 0, the second one is 0, so that should remain unchanged, and 1, 1 finally should go to 0, 1. So, so then the first column is going to be the first one, so that's 1, 0, 0, 0. The second column is going to be the fourth one, is this one, so it's going to be 0, 0, 0, 1. This one, 1, 0 is the third one again, 0, 0, 1, 0. And finally, the last one is the second one, so 0, 1, 0, 0. And we see they're the same, right? They have, so 4 divided by 4 is 1, so these matrices are the same, that worked. So that's kind of a more brute force way of doing it. But we can also think a little bit more in terms of a change of basis and show this a bit more simply, and that helps better understand what's happening in the circuit. Okay, so let's go back to our circuit. We have Hadamard, CNOT, Hadamard. So let's see what Hadamard does. So H acting on 0, just at the single qubit level, gives us a state that's 0 plus 1 over square root 2. Remember, H was 1, 1, 1 minus 1 over square root 2. So acting on 0, which is 1, 0, it's going to give me this. And H on 1 is going to give me 0 minus 1 over square root 2. So let's give a name to these. So it's essentially a change of basis. Again, these are two orthogonal vectors. So let's call that the plus and call this the minus. Okay. Now we can think about like what's happening when states in this spaces, right? So if you send states in the computational basis into these two Hadamards, what enters the CNOT, you have states either plus or minus, right? So we can think about the action of CNOT, this CNOT, on plus. So what would it give me? Well, so when you have plus plus, you have 0, 0, 0, 1, 1, 0, 1, 1, etc. So essentially, if the first one is 1, you flip the second one, but you have both 1, 0 and 1, 1. So flipping doesn't change the sum. So this goes to plus plus. If I think about minus plus, minus plus goes to again minus plus, right? The second one comes in a symmetric combination. So we have, we have both -1 0 and -1 1, and they just switch. What about plus minus? So if I have a plus minus, then the second one has this minus sign in it. So the terms that are important are when the first one is 1. So I have 1 0 minus 1 1. So that goes to 1 1 minus 1 0. So that part essentially flips, which is like flipping the sign of the 1 for the first one. So it's effectively like turning the first one into a minus. And finally, minus minus. Again, it's the same story. So here, the first one comes with an antisymmetric combination. So when it has a 1, you flip the sign for the second one, which is like flipping the sign of this 1. So this goes to plus minus. So, and then we have again the action of the Hadamard now inverses that. So in the same way that, you know, we can, in the same way that H0 is plus and H1 is minus, we can show that H plus is 0. So let's just check that. So it's 1 1 1 minus 1. Plus is 1 over square root 2, 1 over square root 2. So that gives 1 0. And H minus is 1. So this essentially inverts that change of basis. So these two Hadamards change the basis from the computational basis to this basis, plus plus, minus plus, etc. And then this thing, is a CNOT, but see, it's the first one controlling the second one in the computational basis. In this basis, it's actually the second one that's flipping the first one. So when this is minus, when this is minus, this gets flipped, and when this is minus, this gets flipped. So that's one way to conceptually understand how the application of these Hadamard gates flips the role of what is controlling, what qubit is controlling what qubit. All right. So let's go back to our main topic for today. And that's, as I mentioned, the implementation of an arbitrary controlled 2-qubit gate. So we want to make something like this. So decomposition. Arbitrary 2-qubit control gate. So suppose we have something like this. So the first one controls the other one. When the first one is 1, here we have an arbitrary 2x2 unitary acting on the second one. So we're going to make use of a theorem that we talked about last time. So the theorem is that this U can be written in general as e to the I alpha. Then we have RZ of beta, so we use this efficient parameterization, RY gamma, so this is the ZY decomposition, and RZ delta. So we take this form for our RU, which is a completely general expression for a 2x2 unitary. Now, a consequence of this theorem is that there are unitary operators A, B, C, such that A, B, C is the identity, and U is e to the I alpha, A, X, B, X, C. So let me just show it by explicitly say what A, B, C are, and then we check that it works. So let's set A to be RZ beta, this guy, and then we put RY gamma over 2. We put B to be RY minus gamma over 2, RZ minus delta plus beta quantity over 2. And we put C to be RZ of delta minus beta over 2. So first, let's check that ABC is the identity. So if I multiply A by B by C, this is a rotation by gamma over 2 minus gamma over 2, so that goes away. Then we have RZ. Again, I have this rotation by beta. This is minus beta over 2. So AB becomes RZ of beta minus delta over 2. And C is RZ of delta minus beta over 2. So we can combine rotations in the same direction. They commute in some sense. The order doesn't matter. So we can just combine the angles, and then this is, again, you rotate by this angle, you rotate by minus that, so that's the identity. Okay, so now let's see what XBX is. So to write XBX, so X is 1, 1, 0, 0. B is that thing over there. So it's a rotation by minus delta over 2 around Y. So let's just put it there, maybe explicitly. So that's going to be cosine minus beta minus gamma over 2 times the identity plus sine times y. And then here it's kind of easier to put an xx. So let me put an xx. X squared is the identity. And then I have, in B, I have another rz. So let's write that. It's like cosine of minus delta plus beta over 2 times the identity plus sine minus delta plus beta over 2 times z, and then I have another x, another one of these 0, 1, 1 zeros. So essentially we see what's happening here. So if I expand that out, x squared we said is the identity. And here we get an x times a y times an x, if I do that multiplication for this term. So x, y, x, it's easy to see what it does. So it's going to be 1, 1, 0, 0 minus I, 0, 0, 0, 1, 1, 0. This times this product over here, which is minus I, 0, 0, I. So this becomes 0, I, minus I, 0. So that's minus y. Similarly here, if I take now this x, with the I, I'm going to get xix, that's just the identity. With the z, I have something like xzx. Let's play a similar game. So it's 1, 0, 1, 0. Z is 1 and minus 1 on the diagonal. So 0, 1, 1, 0. Let's do this multiplication. So first row, first column is 0. First row, second column is 1. Second row, first column is minus 1. Second row, second column is 0. And then if I do again this multiplication, first row, first column is minus 1. First row, second column, 0. Second row, first column, 0. Second row, second column, 1. So that's minus c. Okay, so cosine of minus an angle is the same. Sine of minus an angle has a minus. So essentially the action of these x's is putting a minus sign in front of the sign, which is essentially changing, if I don't have the x's, it's essentially changing the sign of the angles. So xpx, I can say, becomes cosine gamma over 2 times I plus sine gamma over 2 times y, right? You have one minus sign from the sign, but then the two x's that sandwich y give another minus sign. And similarly for z. So can go to the next page for this. Or just, use a shorthand notation. So remember, B is this. So what's the action of these x's does? xbx changes those signs. So xbx becomes ry of gamma over 2. RZ of delta plus beta over 2. Changes that sign. Now I can look at the whole thing. I can look at e to the I alpha a x bx c. So we're saying now e to the I alpha a x b x c is e to the I alpha a, we chose to be rz beta ry gamma over 2. xbx we just found is ry gamma over 2, rz delta plus beta over 2. And finally, c is rz delta minus beta over 2. So this becomes e to the I alpha, rz beta. Combine these, they're both a y rotation, so the angles just add up. Combine these, they're both z rotations, and the angles add up. Betas goes away, gamma plus 2 plus gamma over 2 is, sorry, delta over 2 plus delta over 2 is delta. So that's our u. So this is a consequence of the original theorem that says for any 2x2 unitary, we can have unitaries A, B, C such that A times B times C is the identity, and U is e to the I alpha, AX, BX, C. Okay, so that's a theorem. So we're saying, again, let's write it. Any 2x2 unitary can be written as e to the I alpha, some scalar, A, X, B, X, C, such that A, B, C is the identity. Okay, so that's a consequence of the parameterization we talked about last time. And then in terms of those parameterization, in terms of these rotation operators, we have also explicit formulas for what A, B, and C are. They're these guys, some products of rotation operators, or in the case of C, it's just a direct Z rotation. So let's see how we can make use of this to write our general control U in terms of CNOTs and single qubit gates. So somehow you see this notation, we have those x's, right? And a CNOT is a controlled x. So that's part of the motivation why we constructed it like this. And the beauty of it is that essentially ABC is the identity. So I want to write a circuit when the first qubit is 1, I apply this U, and when the first qubit is 0, I apply the identity. So this allows me to put two CNOTs. So let's say I have two CNOTs. So if the first qubit is 0, the two CNOTs don't act, right? And then what happens if I put an ABC there? So see, U has A, X, B, X, C, right? So when it acts on some initial state psi, first the C acts, then I have the X, which only acts if the first one is 1. Then I have a B here, and then I put an A here. So now if first qubit is 0, then the CNOTs act as identity. So if you put this initial state, first C acts, then B acts, then A acts on it. So it's like ABC is acting on it. And then ABC is the identity, so that doesn't do anything. So that acts as identity. So if the first one is 0, in this circuit, nothing happens to the second qubit. But now if the first one is 1, if first qubit is 1, then what's acting? Well, again, I have first I have the C acting on the input state. Then I have an X, right? A CNOT is a controlled X. It flips. X is the operator that flips. Then I have a B. Then I have an X, right? These act because the first one is 1. And then I have an A here. So what I have is AX, BX, C. And then I can also put a single qubit gate here that essentially acts as 1, 0, 0, e to the I alpha, right? So when the first one is 1, it gives me an e to the I alpha. When the first one is 0, it gives me 1. Doesn't do anything. So then I have this e to the I alpha here. And that's just U times psi in. So this decomposition, essentially this theorem, allows me to just physically, let's say, make the CNOT gate as my only controlled 2-qubit gate. And then a bunch of single qubit operators. These are not controlled, right? The C is not controlled, B is not controlled. I can make an arbitrary control gate. So this is a very useful and powerful theorem in constructing quantum circuits. Now, of course, a more general control gate, which we will talk about next, will have a certain number of qubits controlling a certain number of qubits. So in general, instead of having 1 qubit controlling 1 qubit, you can have n qubits controlling k qubits. So you can have something like this, for example. So these 2 qubits control maybe 3 qubits over here. And then you have some kind of 3 qubit, like 8 by 8 unitary, acting on these 3. if and only if the first one is, the first two ones are both 1. So it's if we have 1, 1, then we go to 1, 1 tensor, let's say U psi in of the last 3. And if anything else, we just act as identity. So that's the generalization of our control gate where 1 qubit controls another qubit. So next time we'll talk a bit more about these structures and try to come up with some decomposition of them again in terms of simpler stuff that we're already familiar with. So that's a good place to stop.